among us our chief guest, Mr. Gaurav Dhawan sir, on virtual mode. Sir has done his Bachelor of Engineering from Institute of Engineering and Science, Indore in 2013. Sir has been working with Cadence design system from 5 plus years. Sir is a principal application engineer at Cadence with relevant experience of 10 plus years in the field of library characterization, circuit simulation. Before joining Cadence, Sir has been working at Synapses, Microchip, Sankar, Semiconductor, and, and also in Samsung as support AE for system.
Okay. Uh, First of all, thank you very much. It's a great pleasure to talk in front of the faculties from where I have studied. Uh, I can see some familiar faces also. It's been quite some time I haven't met. I wish I could be there. Due to business reasons, I have to be here. Uh, Let me not waste any time. We'll get started with the title. So the title of this presentation is Understanding the Design Flow in VLSI Industry. Uh, I've tried to keep things very generic at the moment. If you have any questions, please feel free to stop me at any point of time. Uh, we'll talk some technical aspects also, but this slide is mainly to interact face to face with you people, get very generic things. These are the contents that I would like to cover in this presentation. First, the introduction slide. Then we'll talk about the VLSI design methodology. What exactly is it? Then what are the steps that we follow in VLSI design flow? These are generic steps. We are not going much in details, but just a generic step flow. What are the design flow challenges? Then we'll cover one aspect of the design flow, which is library characterization flow. This is something that I have been working in Cadence from last 5 plus years, and also that's my part of expertise at the moment. Uh, Later, once we finish with the library characterization flow, we'll talk about the type of industries that we have in VLSI and what are the different career roles in VLSI. I think the last three slides that I have put, the last slide talks about the key skills to consider before applying for VLSI jobs. Basically, I wanted to keep these three slides so that the faculty members can communicate this to the students who want to enter the VLSI domain. So I thought that this will be a great platform to interact with faculties on how we can shape the students' minds so that they can enter the VLSI field. So these last three slides are mainly for student that I've kept, but rest of the slides will talk about general design methodology and how library characterization flow works. Please feel free to stop me any point of time if you have any questions. Am I audible? Am I audible? Okay, fine. Thank you. Okay, then I'll proceed. Okay, so the first slide is introduction slide. I think we don't need to spend a lot of time here. VLSI that we already know, it's a very large scale integration. It refers to the process of creating ICs, which we call as integrated circuits, by combining millions of transistors. There was a time when we used to say that we need to combine thousands of transistors, but now an era has come where we are talking about millions of transistors, and that all these transistors are combined in a single chip. That is termed as a VLSI. So the design cycle involves various complex steps. We'll see those steps one by one, and different methodologies are being used for these different steps. So each step has a different methodology. We will talk about library characterization flow, which is a specific methodology for the characterization purpose. Similarly, if we are talking about design phase, then when a designer is trying to design a circuit, they have a specific design methodology. So every step that we talk about has a different methodology. We'll cover only one aspect of that today. So one crucial aspect of VLSI design is the design flow, which we have already discussed, because it gives you a systematic approach on how you can proceed when designing a circuit. It gives you a step-by-step process that will guide engineers, right? So, little more in detail, what is a VLSI design methodology and why do we need it? So, a design flow, which we also call as design methodology in industry, it's a systematic approach And it's a defined process, I would say. It's a defined process that we follow in any VLSI industry. That if any design has to be made, it has to go through these many processes, right, to ensure the efficient and effective development of ICs. So, as I already told, that it compasses all the several steps, including the specification, the design entry, the synthesis, the verification of the design, even the layout of the design, and the last step is the fabrication. So we'll discuss about these steps one by one in the upcoming slide. But these are the major steps, like the design entry has to be there. Then you have synthesis, where you do the optimization of your circuit. Then you have your verification, where you will verify whether your design that you have made, whether it will work as intended for the application or not. So that is your verification. Then once the verification is done, then comes a layout, how the actual circuit will look like when it will be fabricated in an IC. So, and finally the fabrication step. So one of the primary objective of the design flow is to minimize the design cycle time. And I think that's very important aspect because every project that starts in an industry, in VLSI industry, they have a dedicated timeline. So, for example, if we know that okay, uh, next year there will be an iPhone 16, iPhone 17, whatever. So they will be based on 2 nanometer or 1 nanometer chip. So they have a design cycle in place. They have to get the chip ready by end of next year. If the chip has to be ready by next year, then they will have the design cycle ready. But okay, in one for the first few months of the design has to be ready. Then the verification should be done by this stage. So it has a design cycle time. If we don't meet the target, then the cycle is gone. So you'll miss the target and you will end up delaying your product. So it's very important that this design methodology is in place and we have a proper timeline also in place. So any project that we execute always has a timeline. So it allows designers to break down the complex VLSI process into smaller manageable tasks. So any IC that we need to make, it will be divided into small tasks, right? Even a block needs to be divided into small sub blocks. For example, if you have a very big block, then analog will be designed by a different team. Digital blocks will be designed by a different team. When we talk about analog blocks, there will be a separate team who will be designing PLLs, will be designing sense amplifiers. So different team and different engineers have specific block to design. A specific team will be there to do the synthesis part. A specific team will be there for the library characterization part. So every complex VLSI design process is divided into sub-blocks, and every engineer focus on the specific aspects of the design. So by following a well-defined design flow, engineers can streamline the design process. So as I mentioned, it's very important that we streamline this process, otherwise we'll miss the design cycle. So it also reduces the errors and overall enhances the productivity of the design team. So these are the steps that I spoke about. The first thing is specification. So first, at the initial stage, designer have to first think that okay, this is my end product, this is my automation product, or this is going to be my biosense product, or this application is going to go in the field of anything like mobile or laptop, or even your what do you say, for any kind of work, right? So the specification has to be decided. What should be the operating voltage of this chip? What should be the different corners that we need to look at? We'll talk about corners when I mention about library characterization. So what is the operating voltage? What are the different corners that we need to look at? What is the stress that this chip should be able to handle? How many inputs should be there for this chip? So all these specifications will be decided at this stage. Based on the specification, designers, then the design entry will come, that the designers will discuss which all blocks we need to have for this kind of specification, whether we need to add PLLs, whether we need to add inverter cells, how many chain of inverter cells should be there, how many buffers are there, uh, what kind of latches should be there, should we really need a latch or a clock would work. A lot of things are discussed and decided at this design phase. This is the phase where designers, who are the actual circuit designer, they will start designing a circuit and they will check that circuit at different slew load points. What should be my slew? What should be my transition time? So all these things are decided at this stage, at the design entry stage. So once the design is ready, once they have a complete picture of okay, this is how my design is going to be, then comes the synthesis stage. Synthesis stage is nothing but it's an optimization stage to reduce the power performance. Oh, sorry, to reduce the power and improve the performance of the circuit. Let me give you a very simple example of how what synthesis is. So let's say, are you able to see the board? If I write something, is it visible? So let's say this is an AND gate. This is an inverter cell. If you see this, if you see the circuit, let's say this is a flop. It's a D flip flop. This is an AND gate. These are inverters. So let's say this is the design which has been issued by the design entry team. Now what synthesis tool will do is that it will start optimizing this circuit. We don't need this circuit. It will try to reduce the circuit size. Now how it can be reduced? If you see this is an inverter and I have grounded this. So this is going to be my ground. Since this is an inverter, this is going to be at logic 1 and again this is going to be at logic 0 because we have two chain of inverters. If this is going to be at logic 0, your AND gate will always give you a 0, right? Doesn't matter what is the input at this pin. So if your this pin, one pin is 0, your output will always be 0. So what synthesis tool will do, it will basically completely remove this circuit and we'll just put a ground here. This is how a synthesis tool will work. Basically to optimize the design circuit and to improve the performance. Okay. Next step is verification. So once the design is done, now since synthesis has been done, design optimization has to be done. It has to be verified whether this functionality is again this new functionality, whether it matches with the original functionality or not. Right. So all these verification processes are done through functional simulation. Different simulations will be performed to check whether the previous behavior and this new behavior are they same or not. Timing analysis will be done. So timing analysis is something. Let's say this is a chain of inverter going to a flop. This is a clock. So timing analysis is something like, let's say this is your design. This is at 1 nanosecond delay. Your delay of 1 nanosecond. This is a delay of 1 nanosecond. And since this is a clock pin and this is a Q pin, delay of this flop is let's say 10 nanosecond. So for a input A to pin Q, so A to Q delay is 1 plus 1 plus 10, that is 12 nanosecond. So this spec, or I would say this specification has been given by the design team, that this circuit is intended to operate with a 12 nanosecond delay. This delay should not increase. Otherwise, if this delay increases, then whichever block is coming after this circuit, it will not be able to capture the data properly. So this is the kind of spec that is given by design team. And this is what is checked by the timer tool when we say timing analysis. So when we say timing analysis, what tool will do that this is your original circuit. But let's say after the synthesis, if the design has been changed, design has been optimized, and let's say the tool removes these two inverters. After the optimization, what is the new delay? So the new delay becomes 10 nanosecond. So of course there is a change in timing. So whether this 10 nanosecond can give you a proper data or not, this is what is checked by the timing analysis tool. To check whether the timing has been met or not. This is what we call as timing. Then comes the layout stage. So once everything is done, we know that okay, this is my inverter, for example. So for example, design team, how they will design that, okay, this is my inverter with a VDD, VSS, they are pin A and Y. So let's say all the optimization are done, the design is working fine, the timing is also fine. Now comes the stage when layout team will start designing the circuit, how it should look from the chip perspective. So what they will do is that they will take this and they will start drawing the circuit like this. That is my VDD, this is my VSS, this is my diffusion, this is my NMOS, PMOS, this is my NMOS, right? This is my source, which is connected through a metal gate. This is my drain. This is my drain connected through a metal gate. Now gates are connected through metal gate again. So this becomes my A pin, this becomes my Y pin. Right? So this is your actual design of the circuit. So this is just it's a logical representation, and this is your actual layout design, how it will look in the chip. So in the layout stage, layout team will start designing the circuits. And this picture that you see, this is used by the fabrication team. I'll name the companies who are fabs. So this is taken by the fabrication team, and they will start fabricating the circuit. They'll start fabricating the ICs. This is the whole step of the VLSI design flow. We're talking about the challenges. I think I've already spoken that the complexity is too huge. Now we are talking about millions of transistors, and completing the project on time is a big challenge now, because it will require time to market, because there's a short time to market for VLSI products. A lot of demand has been there for ICs. So it's very important that we minimize the time required for each step without compromising on the quality. Now, power management is another big challenge. So as your size of the transistors goes down, the leakage current is going to increase. I'll try and explain it through a simple diagram. This is a basic transistor picture that we have seen in our textbooks. So I'll pick this one. There's a P substrate, there's an P well, there's a source, this is drain, N plus, and here comes the channel, right? This is your silicon dioxide, this is your gate. So channel comes. Now this channel is what we call as the transistor size, whether it's 28 nanometer technology or it's a 16 nanometer technology. So the distance between these two, between source and now what we are trying to do is that we are trying to reduce this width. So when we are trying to make this closer, what happens is that without requiring the external force, this is source and this is drain, this is let's say VDD. So when you apply a high voltage, your electrons are going to get attracted to it. When electrons are going to get attracted to it, it will form a channel, right? And you can have a current flowing through it. And there is a intensity of field. Now what happens is that if you try reducing this size, some electrons are already there. So without requiring this input, your channel is already there, and it will start flowing the current. So that is what we call as a leakage current. So the problem is that this gate will not be able to control this channel anymore, because the size has reduced so much. So this is what we call as MOSFET, right? This is what we call as MOSFET. Now there's a new technology of transistor which we call as FinFET. So in FinFET, it's a 3D structure basically, where the gate is wrapped from all three sides like this. It's like this. So this is my channel. My gate is covering this channel from three sides instead of just from the top. So in MOSFET we are covering the gate from the top, but in FinFET we are trying to cover it from three sides. So that is a change in transistor size. Another technology of transistor that is coming up is gate all around, in which if this is the channel, FinFET is covering it from three sides, and gate all around is going to cover it completely like a wrap, so that it can control the channel better. So these are the different technologies that we have in place. So these are the different technologies that we have. So technology scaling, as I said, right, it's a difficult challenge. Now we see that 2 nanometer chips, some of the industries have already started working on 2 nanometer, 3 nanometer. Now after 1 nanometer, what next? So that is the major challenge, that we cannot scale further. The thing is that we are trying to focus more on the performance. Okay, before starting library characterization, are there any questions? Because now we are going to start on a technical note. Can you give me a minute? I'm getting a call continuously. Okay, sorry. Yeah, any questions till now? Okay, I suppose there are no questions, so I'll just proceed. Okay, so now we are going to talk about library characterization. This is something that I have been working from last, I would say, 8 years, and this is my area of expertise. Uh, so when we talk about library characterization, right, what actually it does is that it creates a liberty file. It's just a simple ASCII file. You can say it's a text file, and it's an industry standard file which contains the timing information. I'll discuss more in details what is timing information, but you can understand that it will contain the details about any cell timing, any cell's power, how much power is dissipated by the cell, what is the delay of that cell, what is the output transition of that cell, what is the capacitance of that cell. All these details are captured in this file for each and every cell that we are going to design in a circuit. So these data that we get we are getting it through SPICE simulations that we are running in the background. Now, when we are talking about libraries, we also call this as libraries, which we call as a text file. So we call it .lib, we call it libraries. Different terminologies are there. So these libraries are generated for different corners. So when I say different corners, it means that a specific chip needs to be operated. It needs to work on different conditions, whether it is working at minus 20 degrees, whether it is working at 0 degree, or it is working at 125 degrees, right? We have to test a chip on different conditions. So the libraries, the data also will change. Let's say a cell, inverter cell, it will have a different delay if it is exposed to a high temperature. The delay will change when it goes to a minus 20 degrees Celsius. So the delay will also change for the cell, right? All these parameters change whenever we are changing the PVT, the process voltage and temperature. When I say PVT, it means PVTs. So this is process, this is voltage, and this is temperature. So when I say process means that it can be a slow corner. It can be a fast corner, right? Slow corner, fast corner means that based on the doping of PMOS and MOS, what we dope, right? So based on the doping, your PMOS and MOS could be slow than usual, or it could be fast than usual based on the doping, right? So these are different corners. Voltage, a specific inverter cell or a flop should work on different voltages based on the application. So different voltages are tested. 0.7 volt, 0.9 volt, 1 volt, 1.1 volt. Different voltages are there, right? Now, it could be possible that a specific application needs to be operated only at 1 volt, let's say. But over a span of time, it won't keep continuing to work at 1 volt because of leakage. The 1 volt will get dropped to 0.9 volt. After a few years again, it will get dropped to 0.7 volt. So whether the design will be able to handle such small voltages or not, this is what we try to characterize. When we say library characterization, we are trying to understand the characteristics of a cell, right? That cell could be a flop, it could be an inverter, it could be a multi-bit flop, it could be a latch, it could be a level shifter, it could be any cell. It could be an IO cell also, it could be a AMS block, it could be a PLL, right? So any kind of block I'm talking about. Now it also needs to work at various temperature, right? It could be 0 degrees, it could be minus 20 degrees, it could be 125 degrees. So now if you see, these are the combinations that we work on. So if you see this 1, 2, this is 4 and this is 3. So 2, 4 and 3. So these are 24. If you multiply this, right, these are 24. So basically we need to have 24 libraries. We need to have 24 libraries which will have data for uh, each and every scenario. So this 24 libraries will have 24 different types of delay for one cell. Right? One library will have 1 ps delay, another library will have 1.1 picosecond of delay. So that will change. This is what we are trying to characterize. We are trying to understand the characteristics of a cell. Right? This is what PVT is. Now, then once we generate this data, how this data is going to get used is what I will explain now. So let's say now we have understood that okay, library characterization means okay, what is the delay of a cell? So as I explained during timing analysis, right? During timing analysis and that if you have two chain of inverters with a flop that okay, it should be 10 picosecond of delay, it has 1 picosecond of delay and 1 ps of delay. So this data, how timer tool is getting this data, it is coming from the .lib. So this library characterization, the output of this flow is a file, ASCII file, text file. This text file is used by different tools. It is used by timer tool because if timer tool doesn't have the data, what is the delay of the cell? Timer tool cannot work. So timer tool needs to get this data from this .lib. Even the PNR, placement and routing, needs this data because it will have details about capacitance of a cell. So all this data is utilized by different tools in the flow. So it goes to timer, it goes to synthesis, it goes to PNR, it goes to DFT also. So different flows utilizes this data. So when we generate these libraries, we are giving these libraries to multiple teams within the same project. These are the basic terminology before I start, like what is input slew, what is output load. I think this everybody knows, but I'll just give a quick info that okay, this is my inverter cell. What is my input slew? The rate at which the input signal is transitioning. What is my input slew? Whether it's a 10 picosecond slew between this point to this point, this is my slew. This is my input slew. Output load, when I say what is the load seen by the cell at the output of this, load means the capacitance. So when I say output load means we are talking about the capacitance. When we say transition delay, that okay, once the input signal was applied, what was the transition seen by the inverter? Since this is rising, the output will be falling in this case. If this is a 10 picosecond of slew, then it will be more than 10 picosecond of slew because there is a lot of delay happening because of the switching activity. So if this is 10 picosecond, it will be 10.1 or it could be 11 ps. So this is your transition time. So this data gets captured in your .lib, the output delay. Sorry, the output transition time. And similarly, the delay, propagation delay is what we call as a delay also, delay of this cell. Now, if this is my input pin A and Y, what is the delay seen by this cell? This data gets modeled in the .lib. Okay. How do we get this data? Okay, now let's talk about some simulations. What are the inputs to the flow? The first thing that a characterization flow would need is the spice netlist. Spice netlist means it's again a text file. For example, am I going too fast? Any questions so far? Hello? Any questions so far? Okay, sure. Okay, so I think now let's talk about the spice netlist. So when we talk about spice netlist, it is again a ASCII file, a text file, and how it looks like is that let's say this is an inverter. This is a logical representation of an inverter, right? Similarly, if I want to represent this circuit in an ASCII file, what I will do is that I will write like this sub-circuit. What are my pin names? My pin name is A, Y, VDD, VSS. My sub-circuit ends here. Now within this sub-circuit, what I have is a transistor name M1, transistor name M2. What are these connected to? Let's say when I say M1 and M2, M1 is connected to drain. I will point all the details like drain, gate, source and bulk. So I will just say drain, gate, source and bulk. and it is connected to my source and bulk is basically VDD, right? Source and bulk is connected to VDD. So I will just say drain, gate, source, and bulk. Similarly, when I talk about M2, I will say drain is again, this is D, right? My gate is, let's say, A, output is Y, right? So my drain gate becomes A. So here gate I will say that it's a A pin. My drain is basically Y, right? So I will just say that my drain is Y. So this is again drain, gate, source is, this is the source is VSS, source is VSS, so I'll just say VSS and VSS. This is a subcircuit. This is the ASCII format. This is the simple subcircuit definition. This is a SPICE netlist. So the same logical thing, what we know, it's written here in the form. This is taken as an input by library characterization tool. Similarly, the technology model file will be taken. Now, when I talk about technology model file, it's a file that we get from Foundry. Foundry means if we are trying to generate the circuit using, let's say, TSMC or Global Foundries or Intel, for example. So, on which nanometer this is based on? It is a TSMC 5 nanometer technology or TSMC 3 nanometer, or whether it's a Samsung 3 nanometer technology, right? So, based on the technology, a file will be given by the foundry. If it is a Samsung 3 nanometer project, then a technology file will be given by Samsung team. But okay, this is a foundry file. Now, what all details are there in the technology model file is that it will have the behavior of transistor. Okay, behavior of transistor, not the cell. Behavior of transistor, how the transistor is behaving, what is the threshold voltage of that transistor, what is the bulk, what are the parasitics in the transistor. All those details will be in the ASCII format file, a simple text file, but that will be given by Foundry. The next file is template file. A template file is something that we generate as part of library characterization tool. So template file is nothing but to tell the tool which arcs needs to be generated. When I say arcs, if this is an inverter, there are two arcs possible. One is A to Y. A to Y arc is when A is rising and Y is falling. Another arc is when A is falling and Y is rising. These are the two arcs possible. So, when we are talking about Liberate, which is a software from Cadence, so Liberate has a patented technology where you don't need to specify the functionality of a cell. Tool itself is able to recognize the functionality and it will generate the arcs automatically without user. So Liberate is able to do it, but there are other tools also in the market where they don't have this technology and you need to give this information. But what are the arcs possible? So once these details are given to the tool, characterization tool, the tool will understand that okay, I need to simulate these many arcs. So now once this is done, another input that you can give is, which is optional, is an existing Liberty file. So existing Liberty file means, let's say you already worked on a project on 5 nanometer, which is based on this circuit. Now the arc won't change, right? The arc details won't change. Only change that will happen when you are migrating from 5 nanometer to a 3 nanometer or 2 nanometer is the data. The delay will change, the pin cap will change, the power numbers will change, but the arc will remain the same. So to extract those arc information, you can use the existing .lib file, which is a 5 nanometer, which you have already characterized. So tool can use that old Liberty file, understand the cell, understand the arcs, and it will use the same arc information for your new technology. So this is an optional thing. But if you don't have that existing Liberty file, user can also define the arcs. Once the arcs are identified, now circuit simulator will perform the simulations. Different simulators are there in the market. From Cadence, a very known Spectre simulator is there. Another vendor also has XPICE. Different kind of simulators are there, right? APS, AFS, Spectre APS, Spectre X. So a lot of simulators are there in the market. So circuit simulator will perform the simulations. Now how it will perform the simulations? Now once it knows, okay, I have these arcs, it will pick the first arc. But okay, if my first arc is A is rising, if A is rising, it means that A has to go from 0 to 1, right? So initially A will be put at 0, and circuit simulator will start analyzing this circuit and it will perform simulations. Well, okay, what should be my input slew, right? If it goes from 0 to 1, tool needs to understand that what is my input slew. Whether it is 10 picosecond, 20 picosecond. So based on the slew, simulator will start simulating that okay, this is 10 picosecond slew. How much slew will I see at the output? Right? So simulator will start simulating these arcs separately. Once this data is generated, then we have different views of Liberty files. One is NLDM, CCS noise, and LBF. NLDM basically means that a library, a .lib will have details only about timing and power. It will not have any other details. When we say CCS means it's a more, I would say, a granular format of NLDM. That it will have details about power, it will have details about timing, but it will have more granular details. Like if I know that okay, this is my output voltage in CCS, tool will see that okay, what is my current at each and every point, right? So tool will capture all these details in the CCS format. In CCS, N stands for noise. So it will also have details about noise format, how my circuit is going to behave when a noise is introduced at the input of a cell. LBF is Liberty Variation Format, which has details about the variation effects. So these variations that we spoke about in the PVTs, right, process, voltage, and temperature, this is something that we can predict. But once the chip is fabricated, if two devices are identical, two PMOSs are fabricated identically, it is not 100% sure that they will behave exactly same. There will be some variations in the same transistors. So those kind of variations are captured in the LBF. So I'm not going in much detail, but just wanted to explain that it contains the variation format based on the transistors. Okay. Any questions so far? This is what I wanted to capture mainly in the library characterization flow. After these, the slides are mainly on the industries that we have in VLSI and what students can do to enter the VLSI field. So I will capture that once we are done with the question answer. I think we can start with the Q&A if you have. You want me to explain the ARC information again about these? Okay. I do have one sample library file also. I can show it to you. I think that will be a very easier way for explaining. I found that file online. You can, even if you search online, you will get that file. But I'll just open it for you and I'll explain it there. Okay. Let me stop sharing my to share. Okay. Is my screen visible? Can you see one file? Okay, so this is a sample .lib file. Okay, you can find it, you can Google it, you will find it. This is what a typical .lib looks like. Okay, these are some library headers. Here you will define what is the time unit, whatever numbers are defined in this file, what is the time unit. So it is in nanosecond. What is the voltage unit? It is in volts. What is the current unit? It is in milliampere. Right? What is the capacitance unit? It is in picofarad. What is the leakage unit? It is in nanowatt. I'll not go into these thresholds. What is the norm process, right? I explained about PVTs, process, voltage, and temperature. What is the process? One means it's a normal process. I think they are not mentioned it due to confidential reasons. Voltage means it is supposed to be working at 5 volts. In usual cases, 5 volt is way too high. We don't work on 5 volts. It will be in less than 1 volt typically. What is the temperature at which this has been characterized? This is 25 degrees, right? And once you scroll down, this is what I wanted to show. Yeah, for example, this. So once you scroll down, you will see that there is a cell. Now this is a BCD XL. I'm thinking this is a flop cell, DFF. So in this is, if you see, there's a pin information. But under this cell block, there is a pin. So the pin name is clock. What is the direction? This is an input pin. What is the cap seen on this pin? What is the cap seen when the input is rising? What is the cap seen when the input is falling? What is the rise cap range? Right? What is the fall cap range? Whether this is a clock, true. So clock true means this is a clock pin. So it's important that we define the clock pins in the library, so that the timer tool, the STA tool, will know that this is a clock pin. Now here you define the internal power. Now I have not discussed about internal power, maybe later we'll discuss, but this is what I wanted to mention about timing. So similarly you have pin CLR pin, you have, let me go to the timing information. Similarly pin D is there. Yeah, pin Q, right? Pin Q is what I wanted to show, but you have a pin Q where the direction is output. Here you see that there's a timing information, there's a timing block, right? So this timing block, if you see here, it says that it's a related pin is clock. It means that this arc is from clock to Q. Similarly, for an inverter, you will have it from A to Y. This arc is from clock to Q. So when clock to Q and timing sense, timing type you can leave. Cell rise here means that we are trying to see how your delay will look like when your output is rising. Okay, cell rise means output is rising. Cell rise means it's a delay. Index 1 represents your slew, different slews. So this is 0.06. Remember we have seen the unit at the top, but this is in nanosecond. So this is 0.06 nanosecond. This is 0.18 nanosecond, 0.42 nanosecond. So for different slews, and this is your loads. So for this set of slews and for these set of loads, what is my delay value? These are delay value in the 2D table, two-dimensional table. So 1, 2, 3, 4, 5. So it's a 5 cross 5 table, 5 inputs for slew and 5 for loads. So you have 25 values here, different values based on these different conditions. So this is a cell rise, basically when your output is rising. Similarly, you will see a case where your cell fall is there, basically output is falling. And for the same set of slews and for same set of loads. Rise transition means when your output is rising, how the transition looks like. So if you apply a 0.06 picosecond, 0.06 nanosecond of slew at the input of clock, this 0.06 nanosecond of slew will become 0.211 nanosecond of slew at the output. At the output means Q pin, right? So this is how your rise transition will look like. Any questions on this file?
Actually, time you show that 0.6 and 0.2. Means you already mentioned this, or means this is because of the behavior of the circuit itself. Because you already mentioned that means that much variation will be there. You already defined in the code.
Yes, that's a good point. So this data, right, what you see here, a 0.06 picosecond or nanosecond, this data will be given by the design team, because design team has already designed this circuit under a certain set of conditions. They already know that under what slew conditions this design is intended to work. So they will know that this design should not work after 1.2 nanosecond or 1.5 nanosecond. It will not work. Or even if it works, there's no guarantee. So they have tested, design team has tested this design only under these range. So they will give you a range. But okay, try different slew load conditions between 0.06 and 0.12. Now you may increase the number of slews here, you may decrease the number of slews, but the range will be given by the design team. Even this load, this data will be given by design team, and we feed these inputs to the characterization tool. So tool will know that what input slews I have to apply and what output load I have to apply to get this data. Does that answer your question? Any questions on this file?
No, sir, you carry on. You
Okay,
continue.
sure. So there are a lot of things that we capture in this file, right? So this is one thing which I wanted to explain because we have already explained this in the on the board. But there are other details also that we capture here. So for example, this is just for timing arc, right? We also capture details about setup. We also whether setup rising, when your output is rising, what is the setup time? Related pin is clock, so it will be under D pin if you see here, right? So your pin is D, your related pin is clock, and this is your hold rising, means what is the hold value. Rise constraint means this is your slew value at the clock, which is 0.06. This is slew value at the D pin. So when your slew and D pin both have same values, what is my hold value? Hold value is 0, which is typically not the case, but this is just for understanding purpose. When condition, if you see here, this when means that what is the state of my side pin. So let me just stop sharing and I'll just reshare my slides again. Can you see 1 minute? Okay. So the different things also that the different details also that we model in the dotlet. For example, power. Right? We have not spoken about power. A very simple example that I will give is uh, there are two types of power that we model. Three types actually. One is your leakage power, one is your internal power, and one is your hidden power. So there are three different powers that we model. When we talk about hidden power, it is very simple. Any change in input, if there is a block and we are giving the input signal, with that change in the input signal, if there is no change at the output, it means that power was consumed somewhere within the circuit, but it did not cause any transition at the output. But the power was consumed due to internal switching activity. Whatever power was getting consumed there, that is called as hidden power because that is hidden somewhere. It's not causing any effect at the output. So that hidden power we model. So that hidden power gets modeled under the input pin in the library. So if I show you again the library, you can check that under the input pins. For example, pin D, right? Pin clock. So under these two pins, clock and D pin, if you see any power tables, internal power tables, those are hidden power tables. That my change in input did not cause any change at the output. Another table that we model is the switching power, which gets modeled under the Q pin that we saw, similar to the timing table. Under the timing table, you will see that there's a power table also. It means that any change at the input has caused some change at the output, and because of this, how much power was consumed within the circuit. That is called as switching power. Another power that we model is at the top of under the cell, which is called as leakage. That without causing any change, any transition at the input, how much power was consumed by the circuit. So there are different leakage powers also getting modeled. Okay. So you can explore more if you just type Liberty file, sample Liberty file, and then you will see that file. In the first header itself will come. You'll be able to see. Okay, now let me scroll ahead and talk about different type of industries that we have in VLSI. So I broadly divide these companies in four categories. One is product-based companies, where the design is done within the company. Employees are given the task to design the circuits. Or even the companies can hire contractors from service-based companies. And once the product is ready, it is just given to the fabs. So typical examples of product-based companies are Apple, Samsung, Qualcomm, Intel. So they have their own products. They just design their circuits and just give it to fabs. Right? TI, Texas Instruments, ARM, Microchip, Cypress. These are typical product-based companies. Another is service-based companies who don't design their own circuits. They may design their IPs and sell their IPs, but they don't design their circuits. They design their circuits for product-based companies. So product-based companies will hire contractors from these service-based companies to complete the projects. And typical examples of service-based companies are Wipro, HCL, SmartPlay, Waferspace, Open Silicon, Sankalp Semiconductor is from where I had started. So it was a service-based company. Then comes the EDA companies. So whichever circuits are being designed, what all softwares being used for those circuits, those are provided by EDA companies. So a typical example is Cadence. So we designed the software to help all these companies to develop their circuits. Apart from designing the software, we do develop IPs also. We do design circuits. So there is a design team in Cadence also, in Mental Graphics also, Synopsys also. But the scope is very limited in design. But the main part is that we provide software to the product-based companies. And once the circuit is ready, it goes to a fab where the actual fabrication process completes. Typical examples of this is TSMC, UMC. Samsung have their own fabs, Global Foundries and Hynix. So you must have seen that we don't have any fabs right now in India because it's a very expensive process. It requires a lot of stable electricity, a lot of water, clean environment. So that is a major challenge in establishing a fab. So we don't have any fab in India at the moment. There have been discussions going on to establish a fabrication unit. This slide was mainly for students when you want to encourage students to get inside the VLSI industry. These are typical roles that you can speak to your students. So design engineer is something that is common across product-based company, service-based company, or a EDA company. The one that you see in green is something that I've already worked on that as my prior experience. So I was an ASIC design engineer. ASIC means a digital design engineer. Then analog layout engineer who will draw the layouts. So that I've worked. Then CAD design engineer and design automation engineer. So that design automation engineer is nothing but through automation, through scripts, writing scripts, you are trying to automate any process to reduce the manual effort. So for example, if you want to draw a layout which will have 10 inverters back to back, so you should just press a button and those 10 inverters should come as it is. So that's a kind of automation. It's a simple example, but there are many things in many different fields that you can do in terms of automation. So design automation engineer can be in analog domain, it could be in digital domain, it can be even in library characterization also. So different, again, for example, library characterization engineer also. So my work is to mainly work with library characterization engineers of different companies. So I work with them to help them with the library characterization generation. So these are the basic design engineer fields. Another is in the support application engineer, which is in EDA mainly. Now this is mainly to support any customer for any product. It could be in terms of simulation, it could be in terms of library characterization, it could be in terms of synthesis, it could be in terms of verification. So we are basically support application engineering support. We are supporting those design teams to generate those circuits. If at all they face any issues with our software, we need to help them, give them some solution so that they can proceed. So the part of AE or application engineer is not only to understand the software but to also understand the design. Because if we don't understand the design, we cannot help any customer with the software. We also sometimes tell the customers to fix the design because many times we have seen that customer design have flaws and customer also sometimes changes their design based on the feedback from AE. Just continuing with what is the role. So my current profile is field AE, field application engineer, which is very similar to support AE, but it requires a face-to-face interaction. We don't interact much on calls. It's more like a visit to customer place, sit with customers, talk about their pain points, know upfront about their project so that we can plan the resources accordingly. So these kind of roles are applicable in both analog and digital domain. Another role in EDA is product application engineer, which is like working with R&D folks and develop the product, develop new features. They work very closely with field A. So if I'm a field A and if I know that customer has a specific requirement of a feature, this feature doesn't exist in our tool today, and customer is doing everything manually, then I can talk to product A that hey, we need this feature in the tool. Why don't you talk to the R&D folks and get this feature in the tool, in the upcoming version of the tool? So this is the product in AE role. We need to interact with field AE people and guide the same to R&D. R&D engineer is something that works very closely with field and product AE. So we work very closely with R&D. And the main job of R&D engineer is to write codes. So that code could be in Python format, it could be in C++, it could be in Java, based on the tool. So they are the coders basically, and the list goes on. So there are a lot of career roles in VLSI. This slide mainly I wanted to keep that what are the key skills we need to have, and what are the best options that we have. So I think when I was part of IPS, I always had an intention that I wanted to be in core domain. Now whether it could be a communication domain or it could be VLSI, I didn't know how I will reach there, but I knew that I wanted to be in the core domain. Now, it was lucky for me that Sankalp Semiconductor had come that year for recruitment. And what I have learned so far is that VLSI is one of the best options for electronics engineer who are looking for core job, because that is the need of the market. And with the right set of skills and with the right guidance, they have a very fair chance of getting into VLSI industry. So the only key skills that they need to have are these three things. They need to understand the physics of semiconductor devices. What is latch up? What is source stream? How a PMOS works? How an NMOS works? What is doping? Like how a basic inverter cell is working. Even we are asked that sometimes. We have asked that sometimes to join new joinees who are trying to come. During interview, we have asked this question: how just explain how this inverter cell works, and people still struggle. So what we expect is that basic physics of semiconductor devices should be clear. Then, if you have some knowledge about probability, it will be good. It's not a key thing to have, but probability is a good thing to know. Then the circuit analysis. I remember when I was interviewing for Sankalp Semiconductor, my written. I just wanted to share that I had I had answered 20 questions. Out of those 20, 19 questions were right. 19 answers were right. I had only one question wrong, and my whole interview was around that one question to solve that one question, which was wrong. And the only mistake I did was that the direction of current was reversed. So my answer was some plus 20 milliampere, whereas the answer was minus 20 milliampere. That was the only thing I did wrong. So you have a very good knowledge on circuit analysis. It doesn't matter you to know everything, but if you know at least digital or if you know only analog, then you will have a fair chance of entering this field. If any student has worked on VLSI project, that is an added advantage. Try to get some internships in any other projects. Try to explore any tool in industry. That will have an added advantage. And then, of course, aptitude and strong interest is very important in VLSI design. Yeah, so this is just a summary of what I was speaking. This is the last slide. Start understanding basic circuit concepts. I would highly encourage teachers to talk to their students and explain them that they need to understand, have basic understanding of the circuits. So like current mirror, differential pair, PLLs, matching devices, what is latch up. They need to understand all these things. Just basic concepts. They don't need to know everything in detail, but if they know basics also, just go with the basic function and output, right? So we don't need to know a lot, because we don't expect a lot from new joinees also. We just expect them to know basics. So clear concept of programming languages like Tcl, Shell, scripting, Python, Perl. If any of the scripting languages are known to your students, it's an added advantage, because let me tell you, not everybody is good in coding in VLSI, because people are so busy with the design. No, everybody doesn't want to code. They don't have time to code. So it's a clear advantage if you know programming languages. So logically, you have to be sound, as I mentioned, right? Digital circuits, just go through digital circuits, how inverter works, how NAND works, how you can convert an AND gate through a multiplexer, how does it work? Like all these questions, right? You have to be logically sound. Now, documentation is something that I think we lack. Even I lacked as part of when I was a student, but I have realized that documentation is a key aspect in any project that we work in VLSI, because every step that we work needs to be documented. So I would suggest that start inculcating the habit of documenting things on PowerPoint, Excel, or Word, because this is very important when anybody enters the VLSI domain. And of course, team player is important. Nobody likes any student who is self-centered. You need to be a team player, because we don't design anything standalone. We work with a lot of people. We work with a lot of big team. So team player is a must. Yeah. Thank you. That's all I had. Any questions?
Sir, can you suggest some tools for library characterization filing?
I'm sorry, I didn't get your question. Could you please
For
repeat?
library characterization filing, sir.
Library characterization what?
Tools to use for library characterization.
Okay, tools to use for library characterization. Okay, from Cadence, it is Liberate. We call as Liberate, Liberate. From another vendor, which is our competition, the name is Prime Lib. Earlier, they used to call as Silicon Smart. So you can look for Liberate or Prime Lib. Okay.
Any more question from? Thank you, sir.
Thank you.
Thank you, sir, for sharing the knowledge journey with us about cadence, circuit simulation, PDK QA, and analog EDA flow automation. Thank you, sir.
Thank you. I will keep the call.
Okay, sir.
Have a good day. Bye.